All right, so let's take a look at probability review. Some of the basic terms associated with probability, we'll start there. The first thing that we could talk about is a trial, and really all that is a random outcome, or a random event, excuse me. So, for example, maybe we flip a coin 3 times. An outcome then is a value associated um, with that random event. So maybe in our specific example here, maybe that's that we get 2 heads. And so a sample space would be the set of all possible outcomes. And so we could, in this particular example, flipping a coin 3 times, um, so we could get heads, 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 tails, heads, tails, heads, tails, heads, heads, um, heads, tails, 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 heads, tails, 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 heads, or tails, tails, tails. And now, all of a sudden, we could now look and see, all right, so the probability of our outcome, right? So the probability of 2 heads, we've got 8 possible outcomes, and 2 heads would occur 1, 2, 3 of those times. So 3 out of 8 would be the probability of 2 heads. All right, pretty basic stuff. Mutually exclusive simply means that there is no overlap, or one way we could think about that, no common outcomes. Another way you might see this written, just kind of depends upon the terminology. You might also see that written as disjoint. The two groups cannot overlap. And then independent simply means one does not affect the other. So one outcome does not affect another outcome. Keep in mind, and I'll make a note here, mutually exclusive and independent are not the same thing. Uh, Things can be independent and not mutually exclusive in the same way that things might overlap and still somehow be independent. So don't assume that those two things are equal. We're telling you the same thing. All right, so some of the probability rules. The addition rule is the probability of A or B, right? That was the, I'll throw it out front here. There's, remember the big word for addition was or. The big word for multiplication was and. So in terms of symbols, that's A or B. And so what we did here was A plus the probability of B. However, one of the things that you have to remember, you have to subtract the overlap. So you got to be careful when you do an and, especially if there is something where an observation could fall into both categories. And we'll see that play out here in just a minute with our examples. The multiplication rule, so this would be the probability of A and B. And here is what the rule says, you multiply. One thing you got to be aware of, though, in order to use the multiplication rule, they must be independent. So you got to be really careful when you use those two rules, addition and multiplication rule, in terms of if things are mutually exclusive for the addition rule and independent for the multiplication. Another rule we talked about, a very helpful rule, is the complement rule. So that just basically says the probability something happens is 1 minus the probability that it doesn't. Right? You might also see AC, that's the complement. You might also see it written with a line over the top. Those are the same thing. So, and that's coming out of the rule that probability sum to 1. So basically, the probability something occurs or doesn't occur is always going to be 1, right? There's a 100% chance it's either going to rain or not rain today. That's the only two options. One of the tricks we learned along the way was if there's an at least 1, it's 1 minus the probability of none. We'll see that in an example here in a second. The conditional probability, so probability of A given B has occurred, and that was a probability of A and B over the probability of B. Right? I like to think about it, that second outcome, that's what's always going to go in the denominator of your conditional. And the rule for independence, right? We talked about before, one doesn't affect the other. If you're ever asked to check for independence of two events, remember that's the probability of A given B has occurred, has to be the same as the probability of A. You could also look at, it could be the probability of B given A is equal to the probability of B. So this time, whatever's kind of comes first in your conditional, that's what's going to be all alone on the other side of the equal sign. So let's do a few examples. So here's we're going to flip a coin 3 times, but the probability that we get heads is 65%. So I guess maybe a trick coin. So find the probability of 3 heads. So in other words, the probability 3 heads, 0.65, 0.65 times 0.65. And when all is said and done, that is approximately 0.27. So the probability we get 3 heads in a row on 3 flips, 0.27. Exactly 1 tail. So the probability of 1 tail. Well, keep in mind we could do heads, heads, tails, or heads, tails, heads, or tails, heads, heads. Well, really what you're looking at, all 3 of those have 2.65s and 1.35, and there are 3 of those, right? We're going to add that up 3 times, so really we could just multiply that value by 3, and the probability that we get at least 1 tail along the way is about 44%. And here's one of the tricks we talked about before, at least 1 heads. So really the long way here, we could get 1 head, we could get 2 heads, we could get 3 heads, but there's multiple ways to get 1 head, right? You could get head, tail, 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 head, tail. There's multiple ways to get 2 heads. We just saw it right above. So the trick here with the at least 1, that's the same thing as 1 minus the probability of no heads. So in other words, 1 minus the probability of 3 tails. So for us, that's 1 minus 0.35 times 0.35 times 0.35. And the probability of at least 1 heads on 3 flips of the coin, 0.957. One of the ways we looked at organizing this data, you could potentially use a table, kind of a two-way table. Very useful for data that isn't too complicated. Larger tables often will be given to you when there's more than 2 categories. A lot of times I know the AP test loves to throw chi-squared involved. They would love to throw out like a chi-squared problem along with some of this probability. And we'll look at a bigger table here in a minute, but let's just get things rolling. A quick reminder. So here's an example. 56% of Americans have a retirement plan. So we'll put retirement up top. So yes, no. And then health insurance will go here. And again, yes, no. What we'll need here, we'll need a total row. I'm sorry I left that out. But the total number of Americans that have retirement will be 0.56. 68% have health insurance. So 56% have a retirement plan. That means 44% don't. 68% have health insurance. That means 32% don't. And then here we go, 49% of people have both benefits. And that's going to allow us to go ahead and fill in the rest of the chart. So if 49% of those with a retirement plan have health insurance, that means 7% have a retirement plan but don't have health insurance. And I'm just getting that by summing those to 56. I know, again, we can go to this row. So we got a total of 68%, which means there's 19% of people again, I'm just, the total of this row right here has to be 68%. So that's just allowing me to fill the gaps in. And then finally, the percentage of people that don't have retirement or health benefits is 25%. So that answers the first question right there, just filling in the table. And then find the probability someone has health if they have retirement. So in other words, probability of health given retirement. So this is just a good chance to work on our conditional rule. So again, the probability of health given retirement will be health and retirement over retirement. So health and retirement was 49%, and the probability that they have retirement is 56%. And as you can see, out of the people that have retirement, most of them do have health benefits, and so this should be a pretty large number, and sure enough, it's essentially about 87%, 87.5% of those with a retirement plan also have health benefits. All right, so that's just a matter of plug into the formula and go. Another way we saw to organize the data in this unit was a tree. When things got a little too complicated for a table, you can try a tree. A lot of times this false positives and whatnot, they work really well as a tree. So here's some information about HIV testing, and the results of this study suggested that if someone had HIV, they were 99.7% correctly tested as positive, and 98.5% of those without HIV were correctly negative. All right, so there's still a chance that you get a false positive and a false negative. And so here's a clinic in an at-risk population, and they think that 15% of the people have HIV. The trick here is you got to figure out that first split along the way. Right? Is the first split, do you have to test positive or negative, or is the first split you have the disease, you don't? This one's just a matter of kind of thinking through it for a minute, and we realize pretty quickly the first split's either you have it, you have HIV, or you don't have HIV. And so according to this, 15% of the people have it, which means 85% of the people don't. And then once we're here, now we can split. We got a positive, test negative, test positive, and test negative. So 99% of the tests were correctly positive for those that had the disease, which means there's a 0.003 chance that someone could have it and test negative. And then if they don't have it, the test is accurate 98.5% of the time, which means 1.5% of the time you get a false positive. So, number one, what's the probability that we get a positive test? Well, if you look here, there's actually two ways to test positive. You could have it and test positive. So you could have it and test positive, or you cannot have it and test positive, and that happens about 1% of the time. That happens. So the overall probability of a positive test here is basically about 16%. Number two, what's the probability that a patient testing negative is truly free of HIV? So this is a conditional, and the trick here is which one do we know is true? Do we know they're free, or do we know they've tested negative? And here we know that they've tested negative. So given that we have a negative result, what's the probability that they do not have HIV? So this will be the probability of no HIV and negative over the probability that they tested negative. So again, here we go. Probability of not HIV and negative was 0.85 times 0.985. And then a negative test can come two ways. You can get negative this way, and you can also get a false negative. So we got to consider both of those. So that's 0.85 times 0.985 plus that 0.15, the possibility that someone does have the disease and they don't test positive. And at that point, just be careful as you input stuff into your calculator. There's a 99.95% chance that if you tested negative, you are free from the disease in this particular case. And then here's one of those two-way tables. Again, I think the AP test, they love to maybe throw something like this at you. You do some probability, and then they'll turn the corner, and all of a sudden you'll do a chi-squared test. So don't be surprised if that happens. Right now, we're not going to worry about chi-squared. We just got out of that unit, so let's just make sure we're good with the probabilities. What's the probability that a randomly selected student is a girl? That's pretty straightforward. There are 251 girls out of a total of 478. So 251 out of 478. If you'd like to turn that into a decimal, that's about 0.525. Really doesn't matter. You can leave it as a fraction if you'd like. What's the probability that a randomly selected student is a boy or likes sports? Here's that addition rule, and this is where we got to be careful. So this would be boy plus the probability of sports, but because of, we can see there's guys that fall into both, or people that fall into both categories, we have to subtract the overlap. You have to remember that with the addition rule. So the probability of a boy is 227. The probability they like sports is 90. And then the overlap there is 60. And that's out of 478. Kind of running out of room, but it should be 257 out of 478. And you can leave it just like that. What's the probability that it's a girl and focused on grades? I would just go straight to the table for this. The probability that it's a girl that's focused on grades is right there, 130 out of 478. And notice I'm not using the multiplication rule here because I don't know if those two things are independent. The nice part is I've got a category for girls focused on grades, so I'll just go straight for that number. What is the probability that a randomly selected student is a girl given that they are focused on grades? So girl, given that they're focused on grades. So one way to think about this, we could do the conditional probability, so girl and grades over the probability that their focus is grades. Another way to think about it, since we know they're focused on grades, we know we're in this category right here altogether. We know the new denominator is 247, and out of those 247 that are focused on grades, 130 of them are girls. So there's another option. And then are the event girl and grades independent? So does being a girl affect the focus on grades, or does the fact that someone's focused on grades, does that somehow relate to their gender? So to test for independence, again, so we would say the probability of a girl would have to be equal to, we're going to test, is that equal to the probability of a girl given they're focused on grades? Well, the nice part for us is we've actually already done that conditional probability. The probability of a girl given grades is 130 over 247, and the probability of a girl was right there in number 1, which is 251 out of 478, and we're just testing to see are those equal. And I'm not quite as sharp with my large fractions as I should, so I went ahead and converted these to decimals, and it was very, very close, but as you can see, they are not equal, so these two things are not independent. So apparently there is some role that gender plays in focus on grades.